My name is Aidan Dabrowski. My research project pertains to the ability of chlorophyta algae to reverse harmful acidification in freshwater systems. During experimentation, I will be exposing the species Chlorella vulgaris of green algae to various acidic conditions and measuring the growth and absorption rates of algae. Seeing as acids, namely carbonic, sulfuric, and nitric acid, alter the pH of freshwater systems through acid rain exposure, immediate action to mitigate the harmful effects of freshwater acidification needs to be contemplated. The preliminary basis of the experiment is to pinpoint the ideal conditions under which algae can most effectively alter water pH into a neutral range as a treatment for acidified freshwater. Due to algae's ability to sequester chemicals and other substances while impacting water alkalinity, Chlorella vulgaris and other species of green algae should be able to remedy the negative effects of acidification. Algae's carbon sequestering properties through the process of photosynthesis and the intake of carbon dioxide increase the pH of a neutral or acidic freshwater solution that they reside in. Therefore, algae can steadily bring an already acidified body of water to equilibrium with the culture at a neutral or quasi-basic level. Using algae to mitigate the effects of freshwater acidification and altered pH levels is a practice most commonly used in controlled lab experiments, with little physical implementation in real-world applications. Such implementations would include water treatments and quality restoration that would reverse the impacts of acid rain. Algae species flourish in alkaline solutions rather than acidic mediums. Oligotrophic species exhibit growth under lower pH levels in freshwater environments, and yet are suppressed under high concentrations of carbon dioxide, essentially targeting other eutrophic species of algae, like Chlorella vulgaris, as the most effective species to mitigate pH levels. Acid rain is attributed to the depletion of soil fertility as well as a major perpetrator of surface water contamination that can lead to the die-off of many organisms. A divot in water pH, which usually ranges from 6.0 to a basic 8.0 from acid rain and carbonic acid exposure, can be devastating for ecosystems, as this toxicity can rapidly travel through trophic chains, ultimately impacting human livelihoods and consumption. However, as derived from various studies, acidic water pHs and high concentrations of carbonic acid can be targeted by algae with its acid neutralizing capability. Considering the natural abundance of algae in freshwater surface systems and the prevalence of acid rain as a major factor leading to water contamination and organismic death, research regarding the use of algae to reverse these harmful effects is needed. Despite several other controlled studies of algae's chemical absorption properties and its ability to alter water pH, there is little research that reflects the real-world implementation of such algae cultures into freshwater systems, as this would require large-scale collaboration with unknown environmental consequences. Such unknowns prompt the question, to what extent does the implementation of Chlorella vulgaris mother culture microalgae within surface freshwater systems correlate with pH and water acidification? Through experimenting with the algae species Chlorella vulgaris matched with environmental factors such as temperature, external pH, and light intensity, among some external pressures faced by natural algal growth, design for an appropriate algae-induced treatment can be perfected. Such a treatment would seek to remedy contaminated surface waters by targeting acidic pHs. To stimulate the exposure of algae to acidified freshwater systems, samples of Chlorella vulgaris were purchased in 50 milliliter vials along with 1 milliliter samples of freshwater nutrient media and 1 milliliter of algae culture salt that were added to approximately 43 milliliters of freshwater. This process was repeated for each sample, and the nutrient water solution was poured within a 50 milliliter Erlenheimer flask with the addition of 5 milliliters of algae culture in each flask. The flasks were then put under an aluminum heat clamp lamp with a 100-watt heat bulb to maintain a temperature range between 24 degrees and 29 degrees Celsius, which was regulated by an electric heating thermostat and temperature controller. The algae samples were kept under stable temperature and light conditions for a period of 21 days, 7 days dedicated to preliminary growth, and 14 days for the purpose of acidification, exposure, and experimentation. Each flask was covered with plastic cling wrap to seal in heat and gases. For samples exposed to carbonic acid and carbon dioxide gas, air tubes from the outlet aerator pump were inserted through the mouth of the flask and further sealed with additional cling wrap. The absorption of algae was measured using dry weight biomass of each sample from each day of the experimentation period, where cultures were drained over filter paper and the remaining algae was weighed on a digital scale. To measure the pH of algae samples after carbonic acid exposure, litmus pH test strips were used to determine a numerical value for the alkalinity or acidity of the algae samples. The appropriate pH growth conditions range from a neutral 7 to a basic 9. Therefore, the desired pH that would be introduced by the carbonic acid mixture would be an acidic 3 to 4. This served as a basis to prove algae's capability to mitigate pH and effectively return the pH of a solution to a neutral or quasi-basic solution in order to support life that resides within these conditions. The aforementioned carbonic acid was administered with a dual outlet aerator pump to administer carbon dioxide into the flask to a desired level of acidification. As can be seen in the provided data table, I have gathered preliminary dry weights of each algae sample as part of a trial run to experiment with appropriate growth conditions before experimentation with acidified solutions. The algae shown in the table underwent identical light, heat, and timing procedures as detailed previously in the methodology. The dry weight procedure was also identical to that detailed in the methodology.